Alrighty, here we are back in our parallel RL circuit. In the last video we looked at increases in frequency. In this one we are going to look at a decrease in frequency. So again, we have an 18 kHz incoming frequency. We are going to decrease that to 8 kHz. With that decrease, just like in the previous video when we had an increase, we are expecting those ohmic values for L1 and L2 to decrease. Remember, they're a multiplication formula of frequency times inductance times 2 pi. If you put a smaller number in, you get a smaller number out. Alright, so again, we look at the math. We originally had 4.52 k ohms for L1. And now we have an inductive reactance of 2.01 k ohms, which is a decrease. And again, we did have 3.17 k ohms for the inductive reactance of L2, and now we have 1.41 k, again, decrease. With both of those values decreasing, and we are going to do that reciprocal formula again to get our total inductive reactance, and since both of those numbers are now smaller, we are expecting that combined value to also be smaller. So it was 1.86 k ohms in our original parallel RL circuit calculation video, and now it is 828.69 ohms, so it has indeed gone down. Now, with inductive reactance, the total inductive reactance going down, we are expecting impedance to go down as well because it is going to be smaller than that smallest value. And since the smallest value is decreased, that impedance will also decrease. And so we look at the numbers, and it was 1.82 k ohms, and now it is 824.13 k, which is indeed a decrease. It's not a huge decrease because 9k is a very large number. So it's going to drive 828.69 to almost to its value. If R1 was a smaller value, we'd see something even less. But because it is a much larger value, more than 8,000 more than the total inductive reactance, we see a very small change. Alright. Now, when we look at current, we're expecting current to be just the opposite of in the total ohmic value of the circuit, which is impedance. So we did have 6.59 milliamps, and now we have a much larger current of 14.56 milliamps. Okay, when we look at our individual branches, again, the voltage to branch 1 and the ohmic value of R1 has not changed. And so we get current by taking voltage divided by resistance. If neither one of those change, we are expecting the branch's current to stay the same. But branch 2 and branch 3, on the other hand, both of those ohmic values went down. So we are expecting those currents to go up. And if we look at them, both of them do indeed go up. One to 5.97 milli and the other to 8.51 milli. Again, if you wanted to do the total current route rather than the impedance route, you could put that into your formula, and you will see, again, that you would put your original 1.33 milli for your branch 1, which is the current through your resistor, which is not changing. And you would add your new currents for branch 2 and branch 3 together, which will give you a total of 14.48 milli. Those squared will give you that new value of 14.56 milliamps. Again, as a double check, we know that it should be larger than our largest value, but not as big as the two added together. And it is indeed larger than 14.48, but not as big as 15.81. Alright, and again, just like before, all of our voltages are going to be the same for our components. Our applied voltage did not change. Each one of our branches only has one component, so the total voltage applied to the branch will fall on the one component. So R1 will be 12 volts, L1 will be 12 volts, and L2 will be 12 volts. All right, next we are going to look at opens in a parallel RL circuit.